All right, welcome back to Unboxing with Steve, and we got something special here. It just arrived. Let's find out what we have. Nope. Let's start over. Okay. And we'll move this to here. And all right, welcome back to Unboxing with Steve. We got something special just arrived, and let's find out what we have here. And what we see, we have, it looks like, yes, a final exam, Math 166, Fall 2019. And it's a beauty. Look at that. Nice ivory color, classic color. It has a really good finish on it, nice feel to it. Classic paper here. And let's see, is it? Let's find out. I always look for it. Yes, it is in fact double-sided. I really like the double-sided test. It really gets a lot more economical. And then when you're turning your test in, it's much lighter, easier to carry. Life is good. This particular year model, the fall 2019, it kind of marked a transition period. And so this was a test where there were 8 questions, but they dropped one. It was a transition from earlier models and where they would not drop any questions. And then, of course, in later, they changed the policies later on. So this is an interesting choice. So we want to get into this test. Of course, we should start by sort of dismantling this test if we want to get into the inside. So we're just going to quickly pry it apart here so that we can get a closer look at the inside. Let's go through it and really enjoy this test. So let's go ahead and we'll start at the very beginning. And it looks like a really long problem for number 1, but if you look, it's really a fairly not so bad. It starts with a collection of true, false, and then we're going to go into the second part. It's about matching. So let's start with our true, false. The nice thing is, look, we don't have to justify anything. We just have to see whether or not something is true. All right, so let's start with number 1. If AN is positive and the terms go to 0, then the sum must converge, true or false. Now remember, when we say true or false, true means always true. Not just like, oh, I can come up with one time it's true. No, every time it must be true. And false means at some time it's not true. And of course, our go-to examples tend to be things which are geometric or harmonic. And in this case, we know, for example, the harmonic sum n equals, say, 1 to infinity. Doesn't really matter what happens to 0. 1 over n. Terms go to 0. That diverges. So this is a false statement. Let f of x be a continuous, positive, decreasing function of x. If the integral f of x dx is some constant c, or some finite c, then the sum n equals 0 to infinity of f of n equals c. True or false? This is actually another false one. Now, see, what we're trying to do is we're trying to get us to be confused. So this is coming to the integral test. The integral test says, look, if the integral converges, then the sum converges. But it's not saying that they converge to the same thing, because there's always a little bit of an error. If you think about what happens on the integral test, what you're doing is you're approximating a sum. And so you have these little rectangles, but then you have these little tiny slivers. And those are actually differences between the sum and the integral. They don't match. They might match once in a blue moon, but generally false, false. If a and bn are positive, and the sum bn diverges, and the limit as n goes to infinity of an over bn is equal to 1, then the sum an diverges. Well, this is, if you look at it, this is limit comparison test. And what it says is limit comparison says, look, if these limits converge, it doesn't matter whether it's 1 or 100 or a tenth. It just has to converge to some number between 0 and infinity. Then whenever one does, the other does. So this is a true statement. If I have bn less than or equal to an, and 0 is less than bn, and if bn converges, an converges. So what's it saying? Well, it's saying, look, this is pretty small. What's true about this? And the answer is we don't know. See, because an could be huge. What do we mean? Well, look, we could say like bn, we could be like 1 over 2 to the n, that converges. But on an, we could just have it be 1. It's certainly true that 1 over 2 to the n is below 1, but this diverges. So this statement is false. So just because if I know something converges, I don't know what happens to something bigger than that. A bigger thing could diverge. Now, if they had switched, if an was the one converging, then bn would have to converge. If an is positive and the sum, negative 1 to the n an, diverges, then the original sum has to diverge as well. Well, true or false? And the answer is true. Why? Well, if this sum diverges, there's only a couple things that could happen. Well, it could be that the terms don't go to 0. All right, well then definitely doesn't diverge. But it could be that the terms go to 0, but maybe like the even terms go to 0 much slower than the odd terms. But the important thing here is if we think about what's happening with the sum an, well, if I just keep the positive parts or the negative parts, it has to be the case that something here did not work. So that's a true statement. All right. Now, second part. So here, what's going on? For each statement, so we have these statements, we want to match the appropriate formula from the list below for the integral that computes the desired quantity. Now, not all formulas will be used, and that's easy to figure out because notice there's 5 statements, but there's 6 formulas. And we indicate the formula by writing the corresponding label in the box. And there's a box here. And we'll assume that f of x is positive and that 0 is less than or equal to a less than b. So our picture here is we have some f of x from a to b. So the volume of the region for a less than or equal to x less than or equal to b spun around the y-axis. So we're spinning around the y-axis. So if we spin around the y-axis, the shape that we form is a bunch of shells. So we're looking for shell method. Well, which one is shell method? Well, shell method says that's the one that has 2 pi, and there's a couple problems have 2 pi. Then x, because x would be the distance, your radius, and f of x is your height. So it's d, 2 pi x f of x. The length of the curve y equals f of x for a less than or equal to x less than or equal to b. What's that? Well, we're looking for arc length. Now, these pieces down here, these are not arc length. We're going to go into more about this in detail. These two actually both look promising. Now, there's one of these is the answer. It turns out it's A. That's formula for arc length. B kind of looks like a formula for arc length. It's actually the formula for arc length if we were in polar coordinates. So this must be the red herring, the one just there to throw us off. All right. The surface area when y equals f of x is spun around the x-axis. So we spin here, and what shape do we form? Well, we form a disk. So we're looking for disk method. And so pi r squared, pi f of x squared. So our answer here is, whoops, sorry, I got ahead of myself. I did volume around the x-axis, that's C. I skipped this one. Surface area when we spin around the x-axis. All right, what's surface area? Well, surface area is 2 pi times your radius times your length. So the length, see this piece right here? It shows up here and here. So these are little pieces of length, 2 pi, 2 pi. Well, what's the difference between these two? Well, one of them is x, one of them is f of x, and they correspond to the radius. So if I'm spinning around the x-axis, the radius would be the function of x. So that should be an f. However, if I'm spinning around the y-axis, then the distance to the y-axis is x, which is here. So that should be e. So D, A, F, C, E. And there you go. That's number 1. All right, let's try number 2. Find the integral log of 1 plus x squared divided by x squared dx. Now, how can we do this? Well, you might think substitution. U equals log of 1 plus x squared, and then we get a x squared, right? Well, not quite. We get a 1 plus x squared downstairs, not x squared. Now, what do we have here? Well, when we look at this, we say, well, it's really like there's two pieces. There's a, and let's sort of write it as two pieces. So there's a log of 1 plus x squared, and then there's a 1 over x squared. And so when you see two things here, and you say, well, substitution doesn't look like a good candidate. There's really not much in the way of algebra, but things multiplying, that says parts. Well, what are our parts? Well, remember, what is that? It says the integral of u dv is equal to uv minus the integral v du. So we have our two pieces. Now the question is, what's the u, what's the dv? Well, the u should be the part that's hard to integrate but has a nice derivative. Okay, clear candidate. Here's our u. The dv is the other thing. The good news is that 1 over x squared, actually that's not so bad to integrate. So we have that du, well, the derivative of this would be 1 over 1 plus x squared times the derivative of 1 plus x squared, which is 2x dx. Integral of 1 over x squared, well, that's the same as x to the minus 2, and if you integrate that, we get that v is minus 1 over x. All right, so we have uv minus natural log 1 plus x squared over x. And then we're going to have minus the integral of v du. All right, well, minus minus makes a plus. The x's cancel. Of course, that just makes them look like bigger x's. But all right, let's rewrite it. So minus natural log of 1 plus x squared over x plus, I can pull the 2 out, integral 1 over 1 plus x squared dx, and lo and behold, our favorite friend, arctangent. You know, it's not really a calculus test until there's an arctangent somewhere in it. So we get plus 2 arctangent of x, and this is an indefinite integral, and so for full credit, we put in a plus c, and we get our beautiful answer. And it is. It really is a beautiful answer. All right, well, let's turn the page. Find the integral, another indefinite integral, dx over x squared, square root of x squared minus 1. Now, what is this? Well, we kind of see what needs to happen because we have a square root involved. And almost always when you see a square root where you have a difference of squares or sum of squares, that says trig substitution. Now, what do we think when we think trig substitution? Well, what we think is we say, well, what are our possibilities? If I see something of the form x squared minus a squared, that's x equals a secant theta. If I had seen x squared plus a squared, we would do a tangent theta. And if we had seen a squared minus x squared, well, we would have done sine theta. But we are in our first setting, x squared minus a squared. So what does that say? Our a here is 1. So x should be secant theta. What is dx? Well, the derivative of secant is secant tangent. So dx is secant theta tangent theta d theta. So we get that the integral of dx over x squared square root of x squared minus 1 becomes, upstairs, you get secant theta tangent theta d theta. Downstairs, x squared becomes secant squared theta. That's our x squared. Square root of secant squared theta minus 1. Well, secant squared theta minus 1 isn't just anything. That's tangent squared. Not a coincidence. That's actually why we choose it. So, what do we have? Well, we get secant theta tangent theta d theta over secant squared theta tangent theta. The tangents cancel. One of the secants cancel, so we're left with 1 over secant, also known as 1 over secant cosine. And that integral of cosine is sine plus c. Now we're not done yet because we want to start, or rather end, back where we started. We started with x's, we have to end with x's. So we say x equals secant theta. So we draw our triangle. Here we put theta in the corner. And so secant theta is hypotenuse over adjacent. So x1. That leaves one side to figure out. And how do you figure that out? Well, you just take the Pythagorean theorem. You take the hypotenuse squared minus the adjacent side squared, and then take the square root, and that'll give you this missing side, square root of x squared minus 1. No coincidence, of course, it matches with that square root of x squared minus 1 at the beginning. That's why we chose it. So, how do we finish? Well, sine of theta. It's the opposite over the hypotenuse, so we end up with the square root of x squared minus 1 over x plus c, and there's our answer, and life is good. Ah, this is a fun test. Fun test. I'm already 3 problems in. And it feels like we're hardly doing any work at all. All right, so let's do a little bit more work. Number 4, we have this chain. It's not just any chain, it's a heavy chain, and it's hanging over a ledge. The chain is 100 feet long and weighs 150 pounds. So yeah, that is a pretty heavy chain. Okay, so it's 100 feet, and this chain weighs 150 pounds. And it has uniform density. That just means that the weight of the chain is the same everywhere we are. Now there's a 200-pound weight at the end of the chain. So this part down here, that's 200 pounds, and we're lifting it up. So the question is, how much work does it take to lift the chain and the weight to the top? So we're going to move it from all the way up. Okay, well, that's not so bad. We have to remember, as we pull up the weight, the length of the chain shortens. So in other words, when it's all at the bottom, we have the full weight of that chain, all 150 pounds. But at the top, there's no chain left. You don't have to hold on to it because it's all upstairs already. So at the top, the chain weighs nothing. So here's what we have to do. Well, let's make a few notes. First off, how much does the chain weigh? 150 pounds is 100 feet long. So we could say that the weight of the chain is 150 pounds over 100 feet, or we could say it's 1.5 pounds per foot. So that's how much the chain weighs. Now, when we're doing a work problem, how do you do work? Well, work is the integral of our force. All right? So we just have to figure out what our force is. Now, when we say force, really we should think of it like a weight. So we're thinking of it as pounds. So how much does it weigh at a particular location? So when we're doing a work problem, one of the things we have to decide is our units. And, well, really, I shouldn't say units, our coordinate system. I like to put 0 in a nice, convenient place. So let's put 0 here at the very top, and we'll put y equals 100 at the very bottom. Oops, 100, there we go. Why do I put it here at the top versus the bottom? Again, it's just a matter of convenience. I get a choice, though. It's always a free choice. So if we do this, let's think about what our weight is at some place in the middle. So what's our weight here at a particular y? Well, our weight, which is, again, our force, is we have the 200 pound. That's this piece, this weight at the bottom. And now there's something else, plus we have to do the chain. Now, how much does the chain weigh? Well, it just depends on how many feet of chain there is. And if we put our coordinates where we start at 0 at the top, there's y feet of chain, and each foot weighs 1.5 pounds, so we can say 1.5 times y, or 3/2 y. So that's our weight. Okay, so we're going to take it from the bottom to the top, so from 0 to 100, 200 plus 3/2 y, and dy. All right, well, that's not so bad. That's the integral. Now that that's set up, we integrate 200y plus we have 3/2 times a half, which is 3/4 y squared. And then we're going to evaluate from 0 to 100. And if you plug in 0, you get 0, so you just need to plug in 100. So we get 200 times 100 plus 3/4 times 100 squared. Well, 200 times 100, that's 2 with a bunch of zeros. In fact, 4 zeros, so that makes 20,000. Here we have 3/4. We'll get into that. Then 100 squared would be 10,000. So if we think about 3/4 times 10,000, this is 7,500. 1/4 of 10,000 is 2,500, then multiplied by 3. So we end up with 27,500 units of work. What are our units? We didn't actually need to say it, but the answer is foot-pounds. Because that's how everything was measured. And there's our answer. All right, good. That's good. That wasn't too much work. Well, maybe 27,500 foot-pounds worth of work. But solving the problem wasn't too bad. All right. Find the area of the polar curve r equals 2 cosine 4 theta, and it looks like they gave us the picture, between theta equals negative pi eighths and theta equals pi eighths. So they shaded it below, so this is our little piece. All right, so what do we have? Well, area. So how do you find area in polar? So area in polar is you go from your first angle to your second angle, so alpha and beta, 1/2 times whatever your function is, squared. Okay, and this is the case where if we don't have a curve within a curve, we always go straight to the origin, which is what we have here. All right, well, what do we do? So for us, we say, all right, we're going to have our angles are negative pi over 8 to positive pi over 8. Now, one thing we could do is we could just go from 0 to pi over 8 and double, because we can see we have some nice symmetry going on over here. 1/2. And now we're going to take our curve, 2 cosine 4 theta, and we're going to square it. So if we square that, 2 squared would be 4 times 1/2 would be 2. So negative pi over 8 to pi over 8 of 2 cosine squared 4 theta. Now, how do you handle cosine squared? Well, the way you rewrite cosine squared is we use our power reduction rule. So remember, what does that say? Cosine squared of x is equal to 1 plus cosine of 2x over 2. So because we have a 2 there, if we just sort of move the 2 across, 2 cosine squared of an angle x is the same as 1 plus cosine of twice that angle. So this becomes equal to the integral negative pi over 8 to pi over 8 of 1 plus cosine of twice this angle, which would be 8 theta. And now we're ready to integrate. So what do we get? Integral of 1 theta, integral of cosine 8 theta. Well, the integral of cosine would be sine, and then we just have to compensate for the fact there's an 8 on the inside, so 1/8. We plug in negative pi over 8 to positive pi over 8. And what do we get? Well, we get pi over 8 plus 1/8 sine of pi minus pi over 8 plus 1/8 sine of negative pi. But sine of pi is 0. Sine of negative pi, also 0. So we get pi eighth minus minus, which is plus pi eighth, also known as pi over 4, 2 pi eighths. And so that's how much area there is in that pedal. Now, if we wanted the area in all the pedals, we could have multiplied by 8 and seen that the answer is 2 pi, but we didn't need that. And so there's our answer, pi fourths. All right, well, let's do another one. Number 6. Find the summation from 1 to infinity, 3n plus 1 over 4, 2n minus 1. Well, what's this? It's a geometric sum, because we see we have nice powers. Whenever we see n in the exponent, that's geometric. So how are we going to do this? Well, probably let's start by just cleaning it up. So this is the same as what? The sum, n equals 1 to infinity, of 3 to the n times 3 over 4 to the 2n times 4 to the minus 1. Now, That's also the same thing as sum n equals 1 to infinity. 4 to the negative 1, I can just move it up. So 3 times 4 would make 12. Then we have 3 to the n. Now 4 to the 2n, I really want to write that as something to the n. And the way we can do that is that 4 to the 2n is the same as 4 squared to the n, which is 16 to the n. So that's 16 to the n. So this then becomes the sum, n equals 1 to infinity, of 12 times 3/16 to the nth power. So this is why it's geometric, because it's a number times some value to the n. Now how do you sum geometric sums? And the answer is that the sum of a geometric series is the following. You take your first term, whatever that turns out to be, divided by 1 minus r. And here, r is your ratio, what you multiply by at each step. In this case, r is 3/16. So what we'll get is we're going to get 12 times 3/16. That's our first term, because we start at n equals 1. So 12 times 3/16 divided by 1 minus 3/16. 1 minus r. Now we could circle this, and that would be an answer, but let's clean up just a little bit more, because there's fractions within fractions. So let's multiply top and bottom by 16, and if we do that, well, upstairs the 16's cancel. We get 12 times 3, which is 36. Downstairs, we're going to get 16 minus 3, because in the second term the 16's cancel, and 16 minus 3 becomes 13. So 36 over 13, and that's our sum. Now, I will say that geometric sums really are probably the most important sums you're going to encounter. So if you're only going to learn one type of sum from taking Calc 2, you should definitely learn geometric. They're going to show up many, many times in your future. All right, number 7. Find the center and radius of convergence for the power series. You do not need to check the endpoints for convergence. All right, well, that one doesn't look so bad. So whenever we're looking for center or radius of convergence, we either use the root test or the ratio test. Here we see pretty nice terms. No real need for ratio test. We're going to do a root test. So we're thinking of this as our a sub n. And so we're going to take the limit as n goes to infinity of absolute value of a sub n to the power of 1 over n. So that's the limit as n goes to infinity of, well, when we take the absolute value, that's going to be 4x minus 5 to the 2n over n to the 3 halves to the power 1 over n. And notice that the only thing that really needs the absolute value is this 4x minus 5, because that could be negative. So if we clean this up, this becomes what? The limit as n goes to infinity of absolute value of 4x minus 5. Then it's 2n times 1 over n, which is squared. Downstairs we have n to the 3 halves to the 1 over n, which I like to write as n to the 1 over n to the 3 halves. Why? Well, because this thing goes to 1. That's one of our basic facts about limits that we know. So we get that our limit is absolute value 4x minus 5 squared. Now, by our root test, this converges if this is small enough, less than 1. So that tells us that, if we take the square root, that we need absolute value of 4x minus 5 to be less than 1. Now divide everything by a 4, because we want that leading coefficient in front of the x to be a 1. So that says that x minus 5/4 needs to be less than 1/4. And we can now read off our answer, because our center is going to be coming from here. Whatever x minus, in this case, x minus 5/4, our center is 5/4. Our radius is this piece. So how far out do we go? So it's 1/4, and that's our answer, and life is good. These are flying. I wish all our exams were this fun. Number 8. Okay, find the volume of the solid of revolution obtained by revolving the region from 0 to 1 and 0 to e to the x cubed. Now, it wasn't marked here, but we could go ahead and mark it here. There's 0 to 1. Here's this curve, y equals e to the x cubed. And we could even say that that's at e. Now, we have to figure out what this volume is. If we think of taking a little slice and spinning, well, that would form what? It would form a little shell. Sorry, not a shell, a little disc. So we're going to use our disc, or if you like, washer method. So, according to that, what we have is that the volume will be the integral a to b, 0 to 1, of pi times our function e to the x cubed quantity squared dx. Okay, so that's what our volume is going to be. Now, how do we do this? Well, we can at least simplify 0 to 1 pi e to the power 2x cubed dx. Now, we have a question. How do we actually integrate this? Let's go back and stare at our problem. We didn't read the second sentence. See, it says, express your answer in the form of a series. And look how they wrote the word series. It was like bolded and italicized, almost as if it's highly suggestive. In fact, it's very strongly suggestive because we see that this is something we don't know how to integrate. But maybe we can write this function as a series. So we know that if we have e to the z, that's the summation from n equals 0 to infinity of z to the n divided by n factorial. Now, I can replace this z by whatever I want. I just have to make sure I replace it over here by the same thing. So, e to the 2x cubed, I'm thinking of 2x cubed now as being my z. That's the sum, n equals 0 to infinity, of 2x cubed to the n over n factorial, which becomes the sum from 0 to infinity of 2 to the n, x to the power 3n, divided by n factorial. So that's nice. Why? Because we can replace this thing we can't integrate by an infinite thing which we can integrate. Because really it's a polynomial, and polynomials are nice. So this becomes integral 0 to 1 of pi summation 0 to infinity of 2 to the n, x to the 3n, divide that by n factorial dx. Now the key idea here is that summation and integration we can switch. So this becomes we'll write a pi out in front, summation n equals 0 to infinity. We have 2 to the n over n factorial. Then we have the integral 0 to 1 of x to the 3n dx. Well, that's not so bad. That's an integral that we can do. So pi summation 0 to infinity, 2 to the n over n factorial, and it's x to the power 3n plus 1. Divide that by 3n plus 1, evaluated from 0 to 1. Now when you plug in x equals 0, you get 0. And when you plug in x equals 1, this becomes 1. And then there's a 3n plus 1. So we end up with pi, and the summation n equals 0 to infinity of 2 to the n upstairs. Downstairs we have n factorial times 3n plus 1, which is a series, but that's perfectly fine because they asked us to give them a series, and that's our answer. That's what the value is. And of course, if we wanted a number, we can get it to any amount of accuracy. We just make sure we add up enough terms. All right, and for number 9, there's no number 9. That was it, just 8 problems. And we were just starting to warm up. That was a little bit of fun, a little bit of good times. All right, so overall, I like this test. Pretty good. Let's we'll write down, Yowie duck. What is that? Oh, Hungarian. Good times. Good times. It's a nice exam. And, well, we'll always have more coming up. So, good times. Thank you for joining me. And we'll see you next time when we unbox the next exam. All right. Goodbye.